Okay, just carrying on from where we were before, we've worked out that the gradient or the derivative of f of x equals x squared at any point is given by the function f dash of x equals 2x. So there we go. So there's the graph of y equals x squared, and there's the tangent at the point 1, 1, and it has a gradient of 2 times 1, which equals 2, and you can see that's exactly what it's doing there. And you can see this point there, the turning point, the tangent at 0, 0, has a gradient of 0, because the tangent would be just that horizontal line across there. Okay, so that's just showing that that's an interesting point. Turning points are what we call stationary points, have gradients or derivatives. The value of the derivative at the turning point is 0. What this means is that we've now got a much easier way of finding the vertex of a quadratic. Don't have to do all of that, finding the axis of symmetry or completing the square. Don't have to do any of that. Okay, let's go on. Some definitions here. The instantaneous rate of change of a function is obtained by that formula. This is the first principles formula. Okay, the resulting IROC is the derivative or differential of f of x. Its symbol has several forms including f dash of x, dy by dx, or y dash. It all means the same thing. Okay, so we can write dy by dx equals the limit as h tends towards 0, f of x plus h minus f of x over h. And that's just rise over run. Okay. Going to just do a couple more examples. We're going to differentiate now this entire thing by first principles. So our first principles formula, we're going to have a look at f of x equals that. F of x plus h, we just substitute x plus h wherever we see x. Okay? And so we're going to do a bit of algebra, do the FOIL here and expand all of this. Okay? And we get all of that. Okay, these two maroon expressions go into the numerator of the formula f of x plus h minus f of x. The denominator is simply just h as always. Okay, so the derivative of f dash of x, that should be f of x there where it's just obscured by my photo there. Okay, substitute the expressions that we got before for f of x plus h and f of x. So we end up with all of this. And if you have a look, you can see a lot of this is going to cancel that with that. And the 5 will go as well. And you'll notice, and there's a 2x there, that'll go with this 2x, because that one will be a positive. A negative times a negative gives a positive, and that will go with that. So this can actually simplify down all the way to that. And you know this is good because, look, we've got some common factors of h. So we're going to get that to simplify even more. Okay, if you have a look, that common factor of h, we're just cancelling one of them. So the limit as h tends towards 0 of this is 6x. That h is going to, 3h is going to go to 0. It's just going to come down to 6x minus 2. So the derivative of f of x equals 3x squared minus 2x plus 5 is 6x minus 2. Okay, last example. We're going to differentiate 4x cubed by first principles. So once again, we're going to make f of x equals 4x cubed. F of x plus h is going to be x plus h all cubed. And doing all the FOIL 3 times gives us all that nonsense, times by 4. Putting it, simplifying it there. Okay, that we're going to put these two expressions into our big formula. Once again there. So it's all going to come out to all of that. And once again, we're going to see some things. That 4x cubed is going to disappear. And everything else has a common factor of h in it. And that's going to cancel with the h on the bottom. Okay? And so this is all going to come down to, see that h will cancel there, 1 will cancel there, there's still that one and 1 there. So as h gets towards 0 of 12x squared plus 12xh plus 4h squared, these bits are going to go to 0 as h goes to 0. And it's just going to leave this 12x squared. So that's our final answer, 12x squared. So the derivative of f of x, where f of x equals 4x cubed, is 12x squared. Okay, that's finished the section there on first principles. You're going to come back and do something on differentiation by rule.